Hello, my dear students. Again with you, Bishoy Salama. I'm your chemistry teacher, and we will continue our lesson for states of matter. We have started this lesson last Thursday, and we almost finished part one from this lesson. Today we will continue together part number two. Part number two is much smaller than part number one, and I think that we will mainly spend only 30 to 40 minutes in that video. It can be easily shown, and you can follow my channel and subscribe also to my channel, the chemistry professor. And you can also activate the bell and the alarming system in order to receive all new videos. So today we will complete our first topic, which is named states of matter. So last time we have stopped here, and we said that pure substances are having fixed and definite melting points and boiling points. What is meant by fixed and definite? That means that the melting point of water is almost 0 degrees Celsius, and that boiling point of water is 100 degrees Celsius. It's a fixed melting and boiling points, fixed only one number, that during the melting process and during the boiling process, the temperature is not increasing or decreasing. It is just at 0 degrees Celsius or at 100 degrees Celsius. That's assured that my substance is water, because as we said before, that every substance is having a unique melting and unique boiling points. And if it was pure substance, we will have a fixed melting point and a fixed boiling point. The temperature will not change during the melting or the boiling process. If you are having a thermometer dipped into liquid water and this water is being boiling, we will find that the thermometer will keep reading 100 degrees Celsius until all water is boiled off. Um, we need to say that we also said, sorry, last time, that melting point of water is 0 degrees Celsius and boiling point of water is 100 degrees Celsius. But if you are having impure water, we will find that the temperature will not be a constant value at the melting and boiling points, and we will also find that the melting point will decrease and the boiling point will increase. That means that if pure water was having a melting point of 0 degrees Celsius and a boiling point of 100 degrees Celsius, if we are having impure water, we will have, for instance, a melting point of -2 and a boiling point of 102 or 103 and -2 or -3. Any temperature below the melting point, but do not go very low like -100, -200, -18. No, only 2 or 3 temperatures below, 2 or 3 degrees below the melting points, or 2 or 3 degrees above the boiling point. Let's go to the next step and the next definition, which is called evaporation. And during our previous lesson, we have discussed together that there is a difference between the boiling and evaporation process. Yes, what is the difference between boiling and evaporation? All I want you to know that boiling occurs at the boiling point, and a boiling is a change from liquid to a gas. Also, evaporation is a change from liquid to a gas, but evaporation is not, we need to say that evaporation is not a must to be occurring at the boiling point. Oh, what are you saying, mister? You need to say that evaporation may happen at a temperature below the boiling point? Do you think that water can evaporate at a temperature below boiling point of water, which is 100? I think yes, this can happen. Someone tell me where it can happen. Yes, I need to tell you, it can happen when you put your wet clothes out to be dried. Yes, mister, when I put my wet clothes outside to be dried, we found that water evaporates. That means that water reaches the temperature of 100 degrees Celsius. Does water reach the boiling point while I'm putting my clothes outside? No, that does not happen. Oh, I can see also that my clothes can be dried even in winter. The temperature is almost below 20 and below 10, and the clothes are being dried. So what happened? What happens here is a process named evaporation. Yes, this does not happen only in clothes. If you left some water in a glass cup for almost 7 days in your room at room temperature, you will find that this amount of water will disappear. That means that water had evaporated. Also, we can find during summer that we are having a very high humidity in air. Someone tells me that today is too humid, today is too hot because the humid today the weather is having a very high relative humidity. What is that humidity? Humidity is water vapor. That means that the temperature outside is 100 degrees Celsius? No, water is evaporated below 100 degrees Celsius. So what happens? How does evaporation occur? If we are having a glass cup like this, and these are the water particles inside the glass cup. Please forgive me for this bad drawing, but I think it's a good drawing, not bad, because I'm using an electric panel as I discussed with you before. Let's go to that particle. That particle is having an attraction forces from all sides. It's attracted to that one and also that one, and from the top and also from the bottom with the particles of the glass container itself. But let's go to that particle for instance. It's having attraction force from the right, attraction forces from the left, and attraction forces from the bottom. But no attraction forces or weak attraction forces with the surface from the top. Almost no attraction force. So what happened? When some air is passing from here, it gives this particle some energy. And when this particle have enough energy to overcome the attraction forces around it, it becomes free one and it escapes. And when it escaped, it was converted from the liquid state to the gaseous state, and so on. So the first surface escapes first, then the second surface, then the third surface, then the last one. So if you are having too much surfaces, we will be having a weak evaporation process. But if you are having less surfaces, we will be having a fast evaporation process. How we can have small surfaces and how we can have large number of surfaces. How we can have that? If we're having a glass cup like this and we are having particles of water, let's consider that we are having a certain amount and certain particles of water. In this cup, how many surfaces do we have? Yes, we had this one, this one, this one, almost seven surfaces. But if you are having the same amount but in a large bowl and the same amount of particles, do you know we will be having almost two surfaces only. So tell me please, which one will be faster in the evaporation process. Yes, evaporation will be faster here. Yes, evaporation will be faster here for sure because it's only two surfaces. But how many surfaces are found here? Yes, someone tell me that this bowl is having a large surface area. Large surface area means small amount of surfaces, surface number one and surface number two. But small surface area exposed, that means we are having too much surfaces under each other. So I will ask you a question, and for sure I will answer myself. Or I can wait your answers in the comment section, please. I will ask that question. If I'm having some clothes and I need to put the clothes outside to be dried, and I put all my clothes above each other, like this, 5 pieces, and on another day or on the same day on another rope, I will distribute my clothes like this. Tell me first, tell me please, which figure will show a faster evaporation process? Figure number two or figure number one? I will wait for your answers in the comments section, and please tell me which figure will be dried first and which evaporation process will be faster and why. It's very important to tell me and why. Let's go back to the evaporation process and see what are the factors that are affecting the evaporation process. Yes, the factors affecting the evaporation process are two factors, which are the surface area, and number two for sure, temperature. Yes, as temperature increase, sure the particle will gain more energy and they can be more energetic and they can overcome the attraction forces more easily, and so they can escape more easily and evaporation occurs. Let's go to the next part, which are the evidence for the kinetic particle theory. Yes, we said in the kinetic particle theory that all particles are moving all the time. We need to be sure about that. Are really all particles moving all the time, especially in liquid and in gases? Yes. A scientist named Robert Brown in 1827 made an experiment, and he assured that all particles, especially in the liquid state, are moving around randomly, as we said during our hypothesis in the kinetic particle theory. So let's see what Robert Brown do. Robert Brown got some pollen grains. Yes, do you know pollen grains? What is meant by pollen grains? Pollen grains are thus just small particles which move from a male flower, if you took that in biology, from a male flower to female flower in order to make reproduction between plants. I am not that good in biology, but this is the information I know. These pollen grains are just very small pieces, small particles. He got these pollen grains and he started to make his experiment. He got like a piece of glass, we name it watch glass, and he put a drop of water on this piece of glass, and then he put the pollen grains into water, and then he tried to investigate by microscope. He found that these pollen grains are moving in random directions. Yes, pollen grains are moving randomly. What can cause pollen grains move randomly? Do you know what is causing pollen grains moving randomly? Yes, the particles of water themselves. If the particles of water were not moving, the pollen grains will not be moving from their places. But this is, we need to say, this is an assurance for water in which their particles are moving randomly. That's why pollen grains are moving randomly. Do you know, if you entered a room, you and your friends, you were almost 7 students, for instance, and you enter just a room containing 100 other students, and these students were moving randomly all time, what will happen to you when you enter that room? Yes, you will be moving also randomly in all directions, because you will be colliding and bombarding with the particles of the liquids which are already moving randomly, so you will also move randomly. Let's go back. Also, the same haphazard movement is observed if a beam of light passes through smoke or dust particles. During night, when you see a car lighting its light, and in this beam of light, if there were some dust in the air or smoke, you will find that the dust particles are moving randomly in all directions. Why they are moving randomly? Because already air particles are moving randomly, and these particles are colliding and bombarding with the particles of air which are already moving randomly. So the smoke particles and the dust particles will move randomly. Yes, this is a proof for the kinetic particles theory we discussed in our last lesson. Another example is the random movement of particles in a suspension. If you have a suspension like orange juice or any, you will find that particles inside this orange juice are moving randomly because they are bombarded and colliding with the invisible water molecules around them. This part we have discussed last time, that gases can be compressed because there is almost large relatively distance between particles, but we also said that liquids is very hard and solid cannot be compressed. Let's go for the heating curve, and this is the most important curve in our syllabus. In all our syllabus, this is the very important curve, and we can learn much from that curve. We can say that we are having a substance that is a solid at room temperature, and as time passes and as we raise the temperature, the solid keeps on acquiring energy, and the temperature of the solid increase until we reach the critical first point, which is named the melting point. Someone asks me, Mister, why do the temperature remains constant at the melting point? Yes, this question came in June 2019, and it was a hard question. Why do temperature remains constant at the melting point? Do you know why? Because as the solid substance temperature increase, particles gain more energy, and when they gain more energy, they vibrate more and more and more until they reaches a maximum vibration. They cannot vibrate more in that state. So what is remaining in order to change the solid into liquids? As they acquire the highest energy amount, and they reaches the highest temperature at that state, at that point exactly, what will be remaining? Yes, the remaining will be the attraction forces between particles. Yes, this reaches maximum vibration and this one reaches the maximum vibration. Yes, we still need to break down these attraction forces. So what will energy do now? What will be the role of the energy given? Yes, the role of the energy given now is to break this attraction force. So the energy given is consumed in breaking the attraction forces between particles, as if it is not given. Yes, I know it's a hard part, but I need you to know that at upon reaching the maximum vibration or the maximum movement, the maximum energy can be acquired in that state, yes, all the given energy will be involved in breaking the attraction forces. So the energy given is consumed. That's why the temperature do not change at the melting and the boiling point. This is like when you gain or get 1,000 Egyptian pounds, for instance, and on the same day you had to spend this amount in anything, playing, eating, or anything. Will your balance at the bank increase? No, your balance will not increase because you have received 1,000 pounds and on the same day you spent this 1,000 pounds. So your balance will not change. That's why melting point is a fixed temperature, and the temperature do not change at the melting point or neither at the boiling point, because the energy given is consumed in breaking the attraction forces as if it is not given from the beginning. Let's continue, please. Here we will find the solid and the liquid states together. If we kept the temperature constant at the melting point, the solid will change into liquid and the liquid will change back into solid because we are keeping the temperature at the melting point. And we knew from the last time that the melting point is the same as the freezing point. Water melts at zero and also water freezes at zero. So if we kept the temperature at zero, the solid will keep on changing to liquid and the liquid will keep changing to solid, but in something named equilibrium. What does that mean? That the rate by which solid is changing to liquid is equal to the rate by which liquid changing into solid. You will find that there is no change. If you kept the temperature at exactly the melting point, you will find that almost the amount of solid and the amount of liquid are the same. Why? Because solid is changed into liquid and liquid is changed into solid again with the same speed. This is like when you go to a mall and you find an escalator. This you used to do it when you were young. If the escalator is going down, you tell your parents, yeah, I want to go up on that escalator. When the escalator is going down with a certain speed and you go up with the same speed of the escalator, tell me, if one of your friends is standing far away and he is looking at you, do you know he will see you not moving? He will see you constant in your place, standing in your place. This case is called equilibrium. Yes, if we reached the melting point and we kept the system at the melting point, the ice will change into water if you are talking about water, and also water will change back into ice with the same speed. Okay, we will keep rising the temperature and water will change solid, ice will change all into liquid, and starting from that point to that point, we will be having the liquid state by raising the temperature. Yes, as what happened during the solid changing into liquid, that will happen also from liquid to gas. All I want you to know, and he will ask you about that. Why is the boiling point constant? Yes, because the liquid particles has reached the maximum moving at that state. And then the energy given will be only consumed in breaking down the attraction forces. So the temperature will remain constant and liquid will change into gas. And if we kept the temperature at the boiling point at 100, liquid will change into gas and gas will also will change into liquid, and we will having this symbol named equilibrium. This lesson will be discussed in details, but in the topic of reversible reactions. It's not very important in that topic, but all I want you to know that solid changes into liquid and liquid changes into solid at the melting point, and also at the boiling point, liquid can change into gas and gas can change into liquid. And if we kept on raising the temperature, the substance will change into the gaseous state and will keep gas forever because there is no state after the gas. I need to ask you a question. I need to know if this substance was impure, what will be the drawing or the curve at the melting point? I told you that it will not be a fixed point. Fixed point, that means if we extended a line from that constant curve, we will find it hitting the y-axis in a certain number, in a certain point, that he is extending that line and having here a fixed point. But if the substance was impure, we will find the melting point like this. Yes, the melting starts at a certain point, and by the end of the melting point, we are having another temperature. That means that during the melting process, there is a range of temperatures. There is a range of temperatures at the melting point. So it's no longer named melting point, it's melting range. It's not a fixed melting point. And it also may start below that point because if it is impure, melting point decreases, but boiling point, yes, increases. The line will be inclined, will no longer be constant line. Let's go to some easy questions. We look at the table and ask ourselves, carbon dioxide is a gas at room temperature, iron is a solid at room temperature, water is a liquid at room temperature. One substance which can be easily compressed at room temperature. Yes, I can hear someone telling me gas. Yes, it's carbon dioxide. One substance which consists of particles which are far apart at room temperature. Far apart, yes, the mister told us last time that particles are far apart because they are having too much energy and low attraction forces. Yes, this is the gaseous state. So it is also carbon dioxide. One substance which has a fixed shape at room temperature. Fixed shape is only solid, which is iron. Let's go to the second application, which was performed and assured the kinetic particle theory, which something so-called diffusion. Particles are diffusing. I think you heard that wording before. What does that mean? That means that if you were sitting in a room and your sister or your brother was sitting in that corner and you were sitting in the next corner in that room, the opposite corner, and you hear you sprayed some perfume, only one puff of perfume. After a while, your sister or brother will smell the perfume, even if he was outside of the room. What happened? Yes, we can imagine that the particles of the perfume had migrated from that side to that side. The migration of particles proves the kinetic particles theory. How, mister? How do the migration of particles prove the kinetic particle theory? How? Why are the particles moving from the place I sprayed the perfume to the place which perfume was not found? Yes. What? What happened? It has only one reason. Is what happened. In this room, we are having particles of air moving randomly in all directions. Particles of air moving randomly in all directions. And what happened to the particles of perfume which you sprayed from a while? You sprayed the particles of perfume here. Tell me, please, again, as I told you during at the beginning of the lesson, if you enter the room, you were 10 friends holding together hands, holding your hands, and you enter the room containing 1,000 students, and all these students are moving randomly like zombies, moving randomly in all directions. What will happen exactly to you? The 10 friends holding their hands together, what will happen? Sure, they will not no longer be holding hands. Sure, they will be spreaded in the room in all direction. Sure, they will be bombarded by those zombies moving in all direction. So they will spread in the room. You will be one time at that corner and another time at another corner and one time in the center, and you will be moving in all directions. That's exactly what happened. These perfume particles were very concentrated here. They were beside each other, holding together hands like you and your friends. This is the region of high concentration. And suddenly they found those zombies, those particles of air moving randomly. What will happen? They will bombard and collide with the perfume particles, and suddenly, and they will be bombarding with them, and after a very short time, you will find that the particles of perfume will be spreaded in all direction, and they will be splitted from each other. They will no be longer holding hands and very close to each other. They will be spreaded and mixed with the particles of air, and that's why they will reach the other corner. And if someone's sitting here, he will smell the perfume. So they moved from the area of high concentration to the area they were not found, which is the area of low concentration. This is called diffusion. Let's go back. What is diffusion? This is spreading out and mixing process. This is seen mainly in gases and liquids. I will ask you the next question in the comments section. I need to tell you that if you answer those questions right, there will be surprises for you. I'm talking seriously, okay? But let's um, proceed again. Why is diffusion only seen in liquids and gases? Why it's not seen in solids? This is the second question you can answer in the comment section. The particles of one substance mix with and move through the particles of another. As we saw in our example, diffusion goes until the mixture is uniform. What is meant by uniform? There is even distribution. All particles were evenly distributed through the other particles. In other words, we can say that diffusion is a movement of particles from region of high concentration to a region of low concentration. Tell me first, what are the factors affecting diffusion? Yes, there are two main factors affecting the diffusion process. I think one of those factors is temperature. Is the temperature affecting diffusion? Yes, I think. Tell me, please, can you smell a barbecue from afar away or not? Can you know that there is a someone making barbecue from if you were far away or not? Yes, it's possible to smell the smell of hot food. It's possible. But I need to tell you that it's impossible and it's not very easy to smell the smell of cold food. That is not possible. I don't think that one time you said, "Yes, mother, I can smell someone eating cheese in the 10th floor of our building." I don't think you said that before. But I think, yes, oh, someone is making barbecue. Someone is making anything hot. We can smell it. Do you know, if you woke up in the middle of the night and you need to eat something without no one can knows, you must not put this food in the microwave. All home will know that you are making food, because the particles will gain more energy and the particles will be hot, having high temperature, more energetic, can move faster, so they can diffuse faster. Moving faster causes a faster rate of diffusion. But if you need to eat anything during night without anyone can knows, you can eat something cold, because particles are not energetic, so particles will not move faster, so will not diffuse faster, and will diffuse slower, so it will take much time for spreading, and it may be easier, difficult for someone to smell this cold food. So what is the next factor that affects diffusion? Yes, someone can tell me from the kinetic particle theory, we said that lighter particles moves faster than heavier particles. Yes, it is the molecular mass of a certain substance, molecular mass, the mass of the particle. As the mass of the particle is small, the faster its rate of diffusion. Let's go to the next experiment, in which we need to know what exactly happened. They got this jar and they put some bromine liquid at the bottom of this jar. After a while, they found the jar full of bromine vapor. Oh, what happened? Here, two processes have happened. What are they? The first one is the bromine liquid has evaporated and changed into bromine vapor by the evaporation process, even below the boiling point. What happened next? Yes, the bromine particles spreaded and mixed with the air particles and collided with the air particles and moved from high concentration to low concentration by diffusion. All what I said will give you almost 5 marks in your 5 mark question in the exam. This is the second experiment which assures that small particles and light particles move faster than heavier ones. They got this apparatus, and here they got something named cotton wool, like a piece of cotton, only holding a solution named ammonia solution. And from the other side, they got also a cotton wool, like a piece of cotton, and this cotton wool was soaked into a solution named hydrochloric acid. The intention of this experiment is to make ammonia solution evaporates and changes into ammonia gas by evaporation. So we will be having here ammonia gas. And here the hydrochloric acid will evaporate and changes into hydrogen chloride gas. I want you to know, no, do not memorize this equation for now or study it. All I want you to know that when ammonia gas reacts with hydrogen chloride gas, they make a white solid or a white powder. This white powder is named ammonium chloride, but for now You did not yet get this type of equations. So it's the intention of this only experiment to know that when ammonia gas reacts and collides with hydrogen chloride gas, they produce like a white solid. Tell me please, if we met each other on the beach one day and you realize that I am very fat person, I am very fat, and you are a thin and good one. And yes, you said, "Hi, Mr. Bishoy, it's been a long time, did not see you. Hi, X. It's been a long time, did not see you." And we started running toward each other. Do you think where will be the place we will meet each other? Yes, we will meet here, nearer to me. Why? Because I'm fat person, I am moving slowly, and you're a thin person, you're moving quickly. So we will meet at my side. That exactly what did this experiment show. This experiment showed that the white solid was formed beside the cotton wool soaked in hydrogen and hydrochloric acid. When they get the molecular mass of the particles of ammonia and the particles of hydrochloric gas, they found that the molecular mass of ammonia was 17 and the molecular mass of hydrochloride was 6.5. It's almost double the molecular mass. That's why the white solid was formed beside the cotton wool soaked in the hydrochloric acid. That gives us um, a good indication that diffusion depends on the molecular mass. Here is an example for diffusion in liquids. If we are having a purple crystal like a piece of solid of a certain substance named potassium manganate, you shall only know that its symbolic form is KMnO4, and it's not the time for memorizing that substance. But all I want to know that this purple crystal of potassium manganate, when dropped in a beaker containing water, after a while the purple coloration will be spread through water. Oh, what happened? I need 5 marks. I need 5 marks. What happened? Yes, the particles of the water are moving and sliding over each other. The particles of the crystal are bombarding with the particles of water. They are spreading through the particles of water and mixing through the particles of water. So they diffused from high concentration to low concentration, and that you will get the whole 5 marks. Also, another mark can be got like if we can say that the piece of purple, the piece of potassium manganate crystal will dissolve. Dissolve can also give you a mark. As we said, that the rate of diffusion will increase as the temperature increase and also will increase when the particle is lower in its molecular mass. Application for diffusion is how to separate the mixture of gases by diffusion. Yes, we can use the diffusion to separate a mixture of gases. If I'm having, for instance, nitrogen and oxygen in one side of a beaker, and on the other side I have an empty beaker, and this is like a permeable membrane that can pass the gas from one side to another. And if you applied some heat here, I can tell you that the particles which are having the lower molecular mass will pass from this membrane first. So this can be used as a method for separating the gases. Yes, we can separate the components of air by the diffusion process. And the particles which are having, and the gaseous particles which are having lower molecular mass will diffuse first. Yes, if you are having a mixture from helium and argon, helium has a smaller molecular mass, low density, light particles, and so it diffuses at faster rate. Also, we can separate the mixture of air, oxygen and nitrogen, and we can separate a mixture of oxygen and ozone. Someone can tell me which one is having lower molecular mass, lower mass. Yes, sure, it's O2, it's only 2, and O3, it's O3, it's 3. Till that point, we have just finished topic number 1, which is named the states of matter. You shall be doing a homework now, which is solving paper 2 and paper 4 in your classified for states of matter. For any questions, you can contact me in the comments section, or you can text me on WhatsApp. Again, my number is 002 012 018 58910. My name is Bishoy Salama. Thank you and see you next week, before next week, inshallah, in topic number 2, which is separation techniques. Thank you very much.